this is the last video, part 4 in a Electrochem Diploma and Test Prep series, and this is focusing on the end of General Outcome 2, which are into electrochemical applications, both to voltaic and electrolytic cells. So what was covered in the first 2 videos is all the important introductory knowledge for redox in general, and this is the foundation for cells. So if you've not gone through or you don't have a good understanding of General Outcome 1, I wouldn't watch this video series yet. Part 3 was the previous video where we went through voltaic and electrolytic cells and how you figure out the anode and cathode and salt bridge and electrolyte and things like that, and the chloride anomaly. And we're now going to be going through how to calculate standard cell potentials. That's already been done a little bit. How when the reference is switched, the calculation, figuring whether something is spontaneous or not using our table, and then a very different sort of physics-like skill, how to calculate exactly how much mass would be made or deposited at a electrode, or how long it would take to deposit a certain mass. So first, looking at sort of why do we have a certain reference? Why is hydrogen the reference? Or specifically, what would happen if that hydrogen reference was changed? That's what you're going to get tested on. So an old diploma question, if the nickel, standard nickel half reaction was designated as the reference, what would happen to the iron 3+, 2+ half reaction? So in order to switch the reference, we would be subtracting all the data in the table, and we'll be subtracting the E0 reduction of whatever our new reference is. That's what's going to let us quickly re-zero our new reference, and it would let us re-zero everything. So we want the nickel to be the new reference. We're going to subtract, and what do we have to subtract? Everything is highlighted in yellow for this first part, and it was negative 0.26 volts. So we have a double negative, so we just have to add 0.26 volts to any of our half reactions, and that would be the voltage under the new reference. So we can figure out what the value would be for our iron. The old value is 0.77 volts, and we would want to subtract the negative 0.26, or I'm just going to write it as add 0.26 volts. Now, one important thing to realize when we switch something to a new reference, a new zero, anything above that new reference will be positive, and anything below that new reference will be negative. So when we look at this question, because we're asked about the iron 3+, 2+ half reaction, it's above the new reference, so there's no way the answer is going to be a negative number. So it would have to be A or B, and the math that we've done identifies A as the correct answer. That's the new reference voltage, or the new voltage for the iron 3+, 2+ with our new zero. Another question that both lets us deal with calculating cell potential and changing the reference is what I have down below. What would the standard cell potential of a standard lead silver cell be if cadmium was used as the reference? So I'm going to clean off our values, and we'll see what happens if we use not nickel, but cadmium. So I've set everything up in red for this question. So cadmium is going to be our new zero, and that's at negative 0.4 volts. So we have to subtract a negative 0.4 volts to everything, or add 0.4 volts to any of our cathode or anode half reactions. So let's do this both ways. What if we never switch the reference and with switching it? So first off, how do you calculate E0 cell, or the standard cell potential? So So we have E cell, and then we have the naught or zero symbol. That just means under standard conditions. So we're going to have to take the reduction potential at the cathode. Now I like to write it this way: the strongest oxidizing agent will react to the cathode. So it's a reduction potential at the cathode minus the reduction potential at the anode, and it's going to be the strongest reducing agent at the anode. I like to label OA and RA because that's kind of how our table is built. OA is on the left and RA is on the right. So we'll calculate this two ways. Now when you use a standard cell notation, the same as there's standard, or there is cell notation where you do the anode and use a single line and double line and then a single line again. There's a certain sequence to that, and there's a sequence to the wording of a standard something dash something cell. So it's always going to be the anode first and the cathode second, the same sequencing. Okay. And even if you forgot that, the higher up half reaction in your table would be at the cathode, and the lower down standard half reaction would be at the anode. So we're going to have to deal with the silver half reaction first, and we're going to be subtracting from that the lead. So using our table, we can look up these values. We have to look up silver and lead. So again, these are highlighted for us in red already. Silver is positive 0.8 volts, and lead is negative 13 volts. So our silver is 0.80 volts. Now I like to put in the positives just so a student or a teacher never makes a mistake, or it's super clear whether we're talking about a positive voltage or negative voltage. So 0.8 volts, we have to subtract, and then we have to go to the lead, and that was a negative 0.13 volts. Okay. So we have a double negative, so we end up just adding those, and we get a positive 0.93 volts. Now this is a voltaic cell, so you better get a positive cell potential. So what would happen with switching the reference? This will both let us practice switching that reference and let us see what the difference is, or how important is the reference to what the voltage of any battery would be. So our silver is 0.8, and we have to subtract the negative 0.4, which is our new reference, which is equivalent to adding 0.4. So that's going to come out to 1.20 volts with the standard cadmium half reaction as the reference. And our lead is, we have to take the negative 0.13 volts and add 0.4, so we end up with 0.27 volts. Now both of these are positive, both of them are above our new reference. So that makes sense that our math is giving us a positive value. So if we plug those in, we had 1.20 volts minus 0.27 volts, and lo and behold, you get the exact same answer, which makes sense. What mankind picked as a reference should have no effect on what our voltage is. The voltage of this particular battery, of this science, is going to be a little under a volt, no matter what. So if you have a question about switching the reference and they asked about a cell voltage, don't bother switching the reference. But if you're asked about one particular half reaction, then you do have to switch the reference. Okay? So I say half, these are all values for a half reaction. Okay. Let's do another few quick examples of calculating cell potential before we move on. So we have a electrochemical cell, and that's a voltaic cell. We've got two separate beakers of two unique electrolytes. We've got a salt bridge, external cell connecting them, and a voltmeter, not a power supply. So when you have a voltaic cell, you can calculate cell potential really quickly. when you take the reduction potential of the strongest OA, that's always going to be the top half reaction. So you're always taking the top, subtracting the strongest reducing agent. So of course the anode will be your bottom one. So you're always taking the top minus the bottom. So there's not a lot of reason to write a lot out with voltaic cells. Just reminding you of the sort of relationship. We're taking the E naught reduction at the cathode minus E naught reduction for the half reaction at the anode. So the cathode connects to OA, anode connects to RA. So we have 0.34 volts positive. We're going to subtract. And we have a negative 0.76 volts. Now I like to color code my subtraction just so you don't accidentally only write one minus, and then that's going to mess everything up if you're missing a negative sign. So we've got two negatives, a red and a blue. So that'll flip to positive, so we end up adding these. This is a voltaic cell, so there's no way we're going to get a negative cell potential. And the correct answer is going to be a positive 1.10 volts. Voltaic cells are often easier. Electrolytic cells just require going through and figuring out the OA and the RA. It's not as simple as just looking up the two half reactions. So we're going to have to figure out what our strongest OAs and RAs are, and then we can sort of just take the best OA at the cathode minus the RA at the anode. The difference being in electrolytic, the OA at the cathode will be lower and the RA at the anode will be higher in our table, and that will generate a negative cell potential, which goes with electrolytic cells. So we've got to generate a list. We've got a silver and carbon electrodes. So I'm only going to put the silver electrode on my list. I don't bother putting inert electrodes on my list. And then we've got copper nitrate solution. Now I'm going to dissociate this copper nitrate. You always have to do that for your list. We don't need a count, so even though there's two nitrates, I just put the species nitrate on my list. And it's aqueous, so don't forget water. So then I like to label. I always label OAs on top and RA on the bottom. Okay. All elemental metals are reducing agents. Copper 2+ is an OA. Nitrate is not on our table by itself. Nitrate with H+ is a strong OA, but nitrate I'm not going to label because it shouldn't be. And water I will double label. So our strongest oxidizing agent between copper and water is copper. So we're going to need to take that voltage first. So there's our copper that beat out water. So we're going to take 0.340 volts. That's positive. I'm going to subtract, and we've got to figure out what the best reducing agent is. So we have water and silver. Now water is pretty bad, but not the worst, so we should check. And there is our water, but there's our silver. The better reducing agent is our silver. So we're going to have, we have 0.34 at our OA. We'll have that first in our calculation, and we'll have that second. And you subtract these, and you get a negative number like you should for a electrolytic cell, a negative 0.46 volts. So this doesn't happen. It's kind of like needing to go uphill about half a volt. So the minimum voltage you would need, or the minimum battery size you would need, would be a positive 0.46 volts to run this cell. A positive 0.46 volts would overcome this negative potential. Okay. So we've been through most of the outcomes. Last, we can predict whether something is spontaneous from the table, and then we'll end with Faraday's law. So B2.7, predict whether something's going to be spontaneous or not. So I've got two separate reactions. We'll go through them one at a time to see if they're going to be spontaneous. So we've got lead, elemental lead, reacting with iron 3+ ion. So we've got to find these in the table, but we'd want to know which one's the OA and which one's the RA. Now, hopefully you're aware of some patterns that'll help you, but if you totally forgot all the patterns, you can just use first principles. Okay. And we only really need to figure one of the reactants out, because the other reactant will have to be our other agent. So if we look at what's happening with our lead species, it's going from 0 to +2. So it has to lose electrons in order to become the +2. So losing electrons oxidized, that is our reducing agent. Okay. So our iron 3+ better be our OA. We can't have two RAs reacting. Okay. And we could go through the 3+ to 2+ and confirm that is the OA. I'm not going to bother. I pound into my students that you should know that all elemental metals are always reducing agents. There's no exceptions. The metal ions can be either way. It kind of depends. Okay, so now we know our OA and RA. We just have to look at the positioning in the table. So our lead, which is our RA, is here, and our OA, the Fe3+ is there, and it is sort of downhill, or the OA is above the RA. And the higher up you get in the OA column, the better it is, and the lower down in the RA column, the better it is. So this is our OA column, and that's our reducing agent column. So whenever the OA is above and the RA is below, we get a spontaneous reaction. I'm just using a check mark to illustrate that it's spontaneous. Okay. Let's look at the next reaction. We've got elemental chlorine and fluoride, the ion. So again, we have to figure out one of the agents. So I'll start with chlorine, so that's no charge, and it's going negative. So it's neutral becoming negative, so it has to gain electrons to become negative. So GER, gaining electrons reduced, so this is our oxidizing agent. So fluoride better be our reducing agent, and if you had time on an exam, you could double check that. If you don't have time, just find one of the agents. So let's see what type of sequence we have here. The OA is chlorine. Okay, we've got to be really careful. We're looking up reactants. We're being very clear with chlorine versus chloride. Okay, so chlorine, Cl2, is there, and our fluoride, we have to go up to it, or sort of uphill. Or this is not going to happen all by itself, because the OA is lower. We have to go up to the RA. This is non-spontaneous. We would need a battery and electrolytic cell to make this reaction occur. Okay. Now, one sort of higher mental activity type question that is often given is, here's some extra information, put it on your table, and then use it. And that's what this bottom question, I will call it the B question, though it's not a follow-up, it's just a second one, is all about. We're going to take some extra information. So let's see, an experiment concluded that some unknown new metal ion, or we don't know what it is, has a cell potential of 0.25 volts. Well, we don't know what it is, but we can put this in our table. Let's see, where would it go? There, in between those two is where 0.25 volts would go. It'd be below the copper, standard copper, but above the sulfate H+. So I'm going to put a line right there. That's where our 250 volts would go. We would have the metal ion on this side, not enough room to squeeze it in between, and on the OA side, and would have the elemental version of this metal squeezed just underneath the copper. So would the elemental form of this metal, so that would be the Ra version of the metal, which would be right on that red line, react with hydrochloric acid? So HCl is not on our list by itself, but that is a strong acid, which is going to ionize 100% and give us H plus and Cl minus. Now H plus is on our list. There's H plus. Now H plus is our OA, and it is uphill to our new or undefined metal. We don't know what it is, but we know where it is on our table, and it would not spontaneously react. You could put hydrochloric acid into a container made out of this new metal, and it would be totally fine. It's a non-spontaneous reaction. So again, about 25% of your diploma questions will be higher mental activity, and this would be an example of a higher mental activity question. It doesn't have to be hard, but you're taking information, using it, adding it to what you already know or have in a table, and answering a question based on that. So all that's left in electrochem is a very different skill, using Faraday's law to calculate either time or mass of something that's deposited. Now, there's really two sequences that you could get in calculating mass, amounts, current, time in a voltaic or electrolytic cell. So I want to lay out a pathway you're always going to take. Now, the pathway could go right to left or left to right. Now, current multiplied by time, so current would be in amps, time would be in seconds, divide by Faraday's constant, that's on page 3 of your data booklet. Okay, that will give you moles of electrons. So N for moles and subscript E minus. Or if you knew moles of electrons, you could use that with the current or the time and figure out the missing I or the missing T. Now, in order to get from moles to maybe some metal, maybe there's silver being deposited, well, you can convert moles of electrons to moles of whatever you're asked about. I'm just going to put a question mark, but maybe that's silver, or in the question below it's going to be copper. And if you know moles of any element, science 10, you could figure out what the mass of that is. Okay? So this is kind of our potential pathways, you know. Moles is mass over molar mass, so that's how we can flip between the two there. And between moles of electrons and moles of our metal, we need the half reaction for that particular metal. You don't need the whole chemical reaction, and sometimes the diploma gives you the whole reaction, and you just need to find the half. Don't try to break that whole reaction down, just look in your table. One year the diploma had a complicated or whole reaction with aluminum, and they asked about the aluminum being made or consumed, and you could just go to your table and find the aluminum half reaction, and it's a 3-to-1 ratio for aluminum. So let's tackle this old release diploma question. So we're asked, what is the time in seconds to plate about 1/10 of a gram of copper onto steel? So we don't care about the steel. We're plating copper. That's what we need. They even gave us the half reaction, and the current is 15 amps, which when we do unit analysis, amps is coulombs per second. So we can solve this, and we just have to realize the sequence, and we're going that way through this sequence. We'd want to start with looking up the mass of copper, then would want to get the moles of copper, then would want the moles of electrons. This is the step off the NIST. Students get moles of one and they never convert it to the other. And then last we can get our time using Faraday's law. So let's start working through this sequence of math. You know, a lot of students will just do the whole thing right in their calculator, one step to the next to the next. So step one, we already know that's right in the question. There's our mass of copper. So we just have to identify it. Next, we want moles of copper. Oh, that's not a new skill. So we'll fly through this quick. Mass divided by molar mass, all metals, come in ones. Now I'm rounding this for the sake of writing it on the board, but you and I kept all the digits in my calculator. So this is moles, and I want to write moles of copper, not just moles. Because I start with the mass, I got to moles of copper, but I got to get to moles of electrons. And if you're not really clear with what the moles are, you can miss step 3 by mistake. So moles of electrons, that's where we need our half reaction, our copper half reaction, which was given right in the question. There are 2 moles of electrons for every 1 elemental copper. Okay? You never use the ion version in self-stoic. So we point 0. And this is where writing the moles of copper will be nice when I do my stoic. I want to get rid of moles of copper, and our half reaction tells us there's 1 copper solid for every 2 electrons. So this helps us set up our ratio correctly, and it kind of cancels the species, and we're left with our moles of electrons. So they're just doubled the electron moles relative to the copper moles. One last step. So current times time divided by Faraday's constant is the moles of electrons. We've got to rearrange this for time. No, I'm not going to show my work. I'll write down below. So we start with moles of electrons. So we have, so this would be just sitting in your calculator. You could just pull that down. Times Faraday's constant. You look that up on page 3 of your Chem 30 data booklet, the nice orange booklet. Not a number we use a lot, so not many have memorized it. That is how many coulombs are in a mole. And then last, we need to divide that by the current. Now the current needs to be in amps. Now an amp just means a coulomb per second. Watch if you're given milliamps. You'd have to kind of get rid of the milli, divide by 1,000. We have 15 amps or 15 coulombs per second. So we have moles of electrons. This is moles of electrons. I just didn't write that. The coulombs cancel. And we're left with seconds on the bottom of the bottom. You kind of have seconds to the -1 to the -1. Those 2 -1s cancel. We end up with just seconds, and this question asked us in seconds. And I get 21.5. The sig figs is going to be 3, and you don't have to worry about sig figs on the diploma. The question tells you to record your 3-digit answer. Okay. And that is the end. And that's the end of this video series on electrochemistry for either unit tests or diploma exams. I hope you enjoyed this series, and please consider liking the channel, liking the video, or subscribing to the channel.